In the study of reaction mechanisms, we can propose what's going on based on our underlying knowledge of the chemistry, and we can even propose mathematical formalisms for what the rate law might be based on those underlying intuitions. But whether we approach the mechanistic problem through the lens of chemistry or through the lens of mathematics, each of these approaches can bring their own biases. And in the case of the mathematical approach, it might even scare us away from ever studying mechanism seriously. So how can we build up the intuition for how a reaction progresses over time, without necessarily going to the curly arrow mechanisms of chemistry, or by starting at the mathematical equations? How can we look at the graphs of how a reaction progresses over time? And how might we run 1,000 experiments on mechanism without ever going into the lab, without ever running a single quantum chemical calculation? My name's Dr. Marc Reeds, and this is an intuition supplement to the lecture series on the practice and pitfalls of our studying organic reaction mechanisms. Let's go. So, in this first supplement, which relates most closely to lecture 1 in the series of studying the practice and pitfalls of studying organic reaction mechanisms, I want to show you a little bit about building up the intuition for looking at how a reaction will progress over time without necessarily knowing a specific chemical example or indeed approaching it through written equations on the page. Before we get to that, then I will be sharing my screen throughout. My first screen share for you right now is to remind you that if you're coming to this video before anything in the course, the entire course on the practice and pitfalls of studying organic reaction mechanisms is available on my YouTube channel, and it's under the playlist Teaching Mechanisms course. We have 5 core lectures, 1, 2, 3, 4, and 5, and we have an introductory lecture to the entire course as well as an outgoing summary of what you should have learned in the course. So if you haven't checked those out already, please do go check the lectures out, give them a like, hit subscribe, and that way you'll get notifications whenever I release one of these supplements. So in building up intuition for studying reaction mechanisms before you go into the lab, without getting scared away by the mathematical formalisms, what we can do instead is to approach the problem using kinetic simulation software. Now, there are many different varieties of kinetic simulation software. What I'm doing in this particular supplement is to approach this through one of the more common open source kinetic simulation software packages that you can download today and follow along with this tutorial, or indeed download and conduct your own experiments at another time. What we're going to be using today, now going past the YouTube series reminder, is a program called COPASI or COPASI, or COPASI, depending on where you're from in the world. I'll be calling it COPASI. But this is the standalone package that you can download onto your desktop machine or laptop, on Mac or on PC. If you go to the downloads page on COPASI, then there's lots of different options for the machine that you have, and you can download the appropriate package. But what is it? It's on the top here, you can see that COPASI is self-described as a biochemical system simulator. So right up front, it gives you a hint that there's a lot of complexity here. You can study reactions that are multi-compartment, highly complex with a lot of different steps. For us as chemists, presuming that's the main audience here, we can use a package like COPASI to study some of the simple reactions that we'll come across in this course and chemical systems that aren't necessarily biological in nature. So if you want to stop now and you're following along, please go and download COPASI and get it set up. What I'll be moving on to next is to share my screen and walk through some examples of how we can use the COPASI package to simulate reaction mechanisms that we might be interested in. Okay, so what you should now be able to see is the open COPASI window on my desktop machine. So what we'll do is we'll walk through how we set up a proposed reaction profile in COPASI, how we can set that up to run a particular simulation over a certain amount of time, and how we can plot that particular experiment graphically. So on the left-hand side of the COPASI window, we have various options here. So I'll close all of them so that you can see here what options are available to us. So there's model, tasks, output specifications, functions, and units. Now, I mentioned up front that COPASI is incredibly powerful and is used primarily for biochemical systems, which are often highly complex in nature. But we can use this software for much simpler systems and indeed instructional chemical systems that are at the core of this fundamental mechanisms course. So from the top down, I'm expanding each of the options and highlighting only those that are absolutely necessary to get off the ground and to try COPASI for yourself. Inside the model sub-tab, we can go into the biochemical sub-tab again, and from the top down there are the option to look at compartments. In our case, we're only interested in studying reactions that are inside a single compartment. We don't want to add any more complexity than that. But going below to the next section, species, if I hit on the word species itself, first of all, what it brings up is this tabular page on the right-hand side, which shows the names of various chemicals that I've added here. So I've already opened a file that I've pre-made and that I will share with you in the description below this video. This is a file I've already opened and made and added in several chemicals that I want to play with and simulate. So I've added A on the first row here. It's inside the single compartment. We're not looking at multiple compartments. We can add units here. I'm keeping this to millimoles per milliliter or molar, so a concentration unit. I'm specifying an initial concentration of 0.1 molar. So what you may have guessed by now is that A is something I want to simulate as a reactant, and 0.1 molar is the starting concentration of A. Simple as that. Below in the second row, I've got chemical P, which I'm denoting as product. And that has a 0 starting concentration because what we want to eventually do, as you'll see as we go through the tutorial, is to be able to simulate the evolution of product for a particular mechanism over time. If you go down from the species subtab and click on A or P or any other chemical that you specify in a third, fourth, fifth or sixth row, then what you'll see is more specific detail for that particular species in the overall reaction setup as you've described it. You can see once again the initial concentration, and we can see where in the process, where in the overall mechanistic proposal this particular species is taking part, where it's shown, where it pops up, if you like. In our case, as we're just about to see, we've got a little bit of a spoiler alert here. There's one reaction we're dealing with in this first example where we've got A specified as an irreversible reaction going to product. If we go on from A down to P, then we can see some more specific details about P as well. But moving on from the species tab down to the reactions tab inside the biomedical tab, I should say, then what we can see here is not the individual species, but the reactions that we are proposing to be part of the overall mechanistic process. I mentioned just a few moments ago, in this case, we're dealing with the simplest reaction that we want to start with. A simple, irreversible, first-order reaction. A single substrate going to a single product. No more, no less. So it's in this reactions tab that we can start to define this. Again, if we hit on this tab on the right-hand side, some tabular information comes up. So we've got one reaction. You can name it anything you like. So I'll call this, let's say, I want to change that and just call it first order I'll leave it at that. If I want to define what the reaction is, I've done in this case A. And to define the reaction itself, you're really just using your keyboard. So if I start that again, I can hit A space dash arrow space P. And what that COPASI will know to do is to notice that it's an arrow, meaning a reversible reaction going to product. What you can also do, which we'll not do as part of this first intuition, is to, instead of doing the dash arrow, you can hit equals, and COPASI will know to pick that up as an equilibrium. So we'll stick to an irreversible reaction for now. If we expand the reactions tab, we can then go into each specific reaction, and more tabular information will come up specific to what we've now clicked on. So we've got this single elementary step, an irreversible reaction of A going to product. Alternative to setting the reaction up as an equilibrium from the outset, you can click this checkbox here to turn it into a reversible process, in which case it will add an extra rate constant to the table below so that you can define a forward reaction and a reverse reaction. I'm going to leave that unticked for now. So we can see the name of the rate constant here, and COPASI will automatically define the units based on the reaction that you've described above. So we've got a first order process. The units of a first order rate constant are per second, and that's why we have per second in this box as shown under my cursor here. We can set the initial value or a particular value for that rate constant here. We'll see a more intuitive way to play with rate constant later on. So up front, we've come from the overall COPASI menu down into model, down into biochemical, first into compartments, which we've more or less ignored, then into the species sub-tab to define all the different chemicals, starting materials and products that we want to be involved in our process. We've then got more specific about the reaction mechanism that we want to simulate. In this case, it's a single step, simple first order irreversible reaction. And if we expand either of these tabs, species or reactions, we can get more specific information about one particular species in the process, or in the case of reactions, one particular elementary step, where we can look more closely at rate constant. So if I close those menus again, then one last thing that I might look at here inside the biomedical tab is this mathematical page. If you look at differential equations, it will start to map out the differential equations that define the overall process and define each elementary step. So this comes to the point from up front in this intuition tutorial that I mentioned, where if you really want to go into the mathematical detail, if that's how you're minded, COPASI will help you do that, and you can look at what COPASI simulates mathematically versus what you might write down on paper, what you might have learned in other traditional mechanism courses. That's just to let you know that it's there. We're not going into that level of detail for this intuition tutorial. But we are now going to move on from the models sub-tab down into tasks. Once again, you can see the true power of COPASI basically through the number of options that are made available to us here. To keep things really simple and to show you again the bare bones of COPASI to get things off the ground, to allow you to very quickly get up to speed with simulating your own processes, we are going to jump straight down to this time course sub-tab here. And if I click on that, what we see on the right-hand side, as for any other thing that we've clicked to this point, we see some more specific information for whatever we've highlighted on the left. So for highlighting time course, on the top left-hand side, what we can do first of all is pick a time. How long do we want to simulate this reaction for? You might pick this based on what you care about. Are you working on reactions that are 5 seconds long, 5 days long, maybe somewhere in between? Try to pick a reaction time that is most relevant to what you're working on, and that's where you really give yourself the hook to then learn more about what's coming next. So I'm going to just set that for 1,000 seconds for our hypothetical case here, purely for instruction, I've personally worked on reactions that are within the range of milliseconds, and reactions that my team have been working on now are in the region of 17, 18 hours. We've seen everything in between. So I'm picking 1,000 seconds here just as a purely arbitrary number. If we go to intervals, the next text box along, then that's essentially how many data points do we want? How many segments do we want our profile to be made up of? And we can subdivide that a little bit further by looking at each data point being mapped onto a certain point in time. So I'm leaving this as one, meaning we want a single data point every second, and we want 1,000 of those. So we're going to have a simulation that's made up of 1,000 data points here. You can also play around with the checkboxes for making this automatic. And there's various other options here. To be quite frank with you, there's many of these options I've never even played with. I've been studying mechanisms for the best part of a decade now, and a lot of what I show you in this tutorial is still what I use to this day to help give me the grounding for a mechanism I want to study and go beyond simply proposing one. Okay, so we've looked at the time course, how long we want to simulate for, and how many data points we want to put in that simulation. If I look at result here, again, I'm giving you a little bit of a spoiler because I've simulated a reaction before. If this is the first time you've opened COPASI, you won't see anything here, but as soon as you run some simulations, you'll then have some tabular data based on time and the concentrations of the species that you're simulating. We'll come back to this later perhaps, but you can hit save. So what you can do is save essentially that data as a text file. I'm not doing that here, I've just shown the tab pops up to allow you to save. But if you save that tabular data as text, and then that text can be read into something like a spreadsheet package like Excel, for instance, and you can start to make your own graphs. So really useful. Let's do a little bit of a mini summary again. We've gone from model, where we essentially define the species and the mechanistic steps we want to simulate. We then go down to time course to say how long is this simulation going to be, how detailed, how many data points are going to be there. Then the next tab that we're going to jump to, ignoring everything else in this tasks subtab, is to go down now to the output specifications. Now I need to open this up, so close tasks above, and output specifications. If I go down to plots, you'll see that I've defined a few already. And then if I go down to those that I've defined, we see more specific information again. This is the pattern to notice with COPASI. You'll have seen it several times by now. Whenever you click on the left, you get an expansion of the detail on the right. So in output specifications, we're inside the plots submenu. And we'll go into the examples I've defined in a second, but if I want to define a third plot, I'll just double click on the third row. And then that opens up a space where I can then define what curves I want to create as I simulate the reaction. If I hit new curve, we'll see the various options of the parameters that can be simulated on the X and the Y axis of whatever graphs we create. I'm first and foremost interested in time profiles. So if I have time on the X-axis, some chemical concentration on the Y-axis, how does that progress over time? How does that temporal fingerprint manifest itself and give me clues to what the reaction mechanism might be under the hood? So inside this time tab for the X-axis, then I'm looking at model time, so the time of the overall process. So I've highlighted that. On the Y-axis options, I want to go into species, and I want to look at the transient concentrations. Again, you can plot whatever you want here, have a play, explore, see what other things are available. I'm showing you the bare bones. I'm showing you what works 9 times out of 10 for much of what I've studied myself and what many others have studied. I'm going to create a plot that covers the concentration, the transient concentration as it changes for the substrate A, the reactant A, and the product P. So I've hit Control each time I click on one of these so that both of them are highlighted. So x-axis is model time, y-axis is within the species tab. I'm looking at the transient concentrations of A and P. If I hit OK, it's then giving me the options to define a little bit more granular detail about how those curves for A versus time and P versus time are shown on the same plot. So for example, if I look at A versus time, I can come over to the right hand side. Let's say I want to define points rather than a line. So I quite like points rather than lines because it gives me a feeling that those could be points from NMR spectra or HPLC traces, or some other analytical technique that gives me a direct measure of the concentration. So I like to do points for that purpose. We can change the width to essentially change the size, the thickness, how easy these are to see. Well, you can see I'm going far beyond what's necessary here. I'm going to set the width to 3. I'll leave everything else as is. I can define the name of the overall plot, so let's call that test plot for intuition lecture. I could go into the subplot for P versus time, do the same sort of thing. So again, I'm going to make that point rather than a line. I'm going to make it a little bit thicker, and I'm going to let the colour be automatic. Okay, so I've defined a plot that I want to come out of this. Now, another little mini summary again, because we're going through quite a lot here. From the start, we've gone into model, then biochemical, not biomedical, biochemical. We've ignored compartments, we've defined the species, we've then defined the elementary steps of the reaction. We've only got one step for a very simple irreversible first order reaction here. We've defined starting concentrations, we've defined starting rate constants. We've then gone into time course to define how long we want the simulation to be, how many data points we want to show in that simulation. And then we jumped straight down to output specifications, and within that, plots, in which we've defined a test plot in this case. And what I didn't show is some of the other plots I'd already made for this particular file. So one that's a little bit different is I've defined one that instead of plotting concentration versus time, it plots concentration versus rate at a given point in time. And that can be a very powerful plot for looking at graphical rate equations, reaction progress kinetic analysis, and other more sophisticated techniques. As before, these have some aesthetic properties that you can define in order to get the plots to look how you want them to. We're now at the point where we can simulate some stuff. We can get some graphs out and start to play with them. This really gets us to the crux of what this is all about. What you're about to see is the pictures that you can play with, change, tweak based on the parameters, and start to build up an intuition for chemical reactions without having a specific example in mind and without having to first go to the mathematical formalism. To run anything in COPASI, what you have to do is go back up to the time course within the tasks submenu. And right down at the bottom, if I just move my window up here, you can see this run button here. So what I'm going to do is I'll hit that right now. And what's popped up are, although they're stacked on top of one another, we've actually got 3 plots that have come out. So there's the one that I made live for you in this tutorial, test plot for Intuition Lecture 1. That is plotting the concentration in millimoles per milliliter versus time in seconds. And the plot has A and P for our simple irreversible first order reaction. A is in red, so you can see that that's decreasing over time. So that makes sense. We've got a reactant. We expect that to be depleted as the reaction progresses over time. And conversely, we have product, or P, in blue, which started, if you remember, when we defined species with a concentration of 0, and we're seeing that evolve positively over time to maximum concentration. equal to the starting concentration of A. So far so good. So earlier I had actually defined the same sort of thing. So there's concentration versus time. This is exactly the same plot. I'm just going to close one of these to keep things simple. And on the alternative plot, I mentioned graphical rate equations. So that's what we have here. So rather than concentration versus time, we have a measure of concentration versus concentration on the x-axis versus rate of formation of product on the y-axis, which is a straight line. We'll come back to the reason for that shortly. Without further ado, it's taken us a while to get here, but this isn't the full story. The icing on the cake, the real power that you can give yourself through COPASI, is shown on this little scroll bar symbol, this little function on near the top file menu for the COPASI program itself. So once you've set up the species, once you've set up the reactions you want to run, once you've set up the time course, and once you've hit run and brought up some graphs, still within the time course highlighted submenu, if you then click on this scroll option, what it will do is bring up another window that has on it the concentration of the starting reactant A, the concentration of product, and the rate constant for that single elementary step. Now, I've already defined these because I think I want to see how concentration affects the reaction. I want to see how changing the rate constant affects the reaction profile. If you hadn't defined any of these sliders, you can hit the new sliders button within this sliders window, and you can bring up all the parameters that you want to play with. Make smaller, make larger, make something intermediate. All the things that you want to be able to play with to change the output graph. And now this is how you can do 1,000, 10,000, 1,000,000 experiments if you so wish, without going into the lab, without writing down a mathematical equation, without doing a DFT or some quantum chemical calculation. This is the tool set of kinetic simulations that can go with all those other things, that will eventually go with the experiments that you run, that you might then overlay real data with this simulated data. These kinetic simulations and those experimental data might then be partnered with quantum chemical calculations to get more molecular insight into why the reaction progresses the way that it does. But using these sliders and watching how the graphs change with those sliders is how you can build up the intuition for what rate constant really means and what concentration really means in terms of how it affects a reaction for a given mechanism. So, assuming that we're fine with what we want on these sliders here, what you could also do is, in this little edit tab within each slider, if you open that up, you can define the minimum and maximum values. So for concentration of A, the minimum value is nothing, the maximum value is 4 molar concentration. You can do the same in product. I'm not changing anything here. And we can do the same in rate constant. Now I've marked this as 0 to 1. I'll maybe change this to 0 to 5. But then what you see is that if I start down here at 0, on the left hand side, sorry, it starts at 0. If I scroll all the way up to the right, it starts at 5. But now you can see that I'm live scrolling here. As soon as I drop that, what happens is that it automatically runs the COPASI simulation again and gives you a new set of graphs based on how those sliders are set for that particular instance. So you'll notice here that one of the graphs popped up again because I've made 3 graphs. I'd closed one to make things a little bit simpler earlier. But every time you run the simulation, however many graphs you have defined, however many plots you want to output, they will all pop up. If you've defined 1 plot, 1 new plot will pop up. If you've defined 5, the full 5 plots will be shown on screen again for every time you run the simulation. So it's running automatically because everything is ticked to run automatically within the sliders. But now at this point, and this is still how I try to build up intuition for myself, I will have the sliders tab on my left. I will have the concentration versus time in the middle, and then I'll have the graphical rate equation on the right-hand side. So what I'm going to do now is, if I leave the starting concentration of A at 0.1 molar, I'll leave the starting concentration of P at 0, so that we're seeing how the product evolves from a 0 starting point. All I'm going to change is the rate constant. So what happens to the profiles of this reaction as I increase the rate constant? So let's start down nearer 0. So it's 0.055 per second. And for the time profile, you see that we've got a reaction profile simulated over 1,000 seconds, just as we wanted. And because we've asked for 1,000 data points, that most of them are close together, you can see those at the fastest point of the reaction because they're most separated. But what looks like a line up at the top here on the blue plot, those are still individual data points, are just so close together that you can't see them. So we've got the reaction overall time simulated as we described earlier when we were doing the setup. If I make the rate constant a little bit smaller, so not 0.055 but 0.025, it's made the rate of formation of product slower than it was before. So I'll move the background tab over a little bit so you can see the live update a little bit more clearly than I was able to that first time. So increasing the rate constant, there we go. You can see now that the reaction is progressing at a quicker rate. You can see that the profiles for the time, the concentration versus time profile are squished further to the left because the reaction is progressing faster. So if I turn down the rate constant again, we can see that the time for the reaction to progress is slowly increasing again. And with one slider highlighted, you can use the arrow keys on your keyboard to more fine tune the rate constant. And so now right down at 0.02, you can start to see how long the reaction might take. Down at 0.01, it's taking even longer. So in the process of talking to you, I've maybe hit these arrow keys 4, 5, 6 times. Think about that as 6 experiments. That's 6 points of feedback you've given yourself to figure out how one parameter will affect a reaction profile given a particular reaction mechanism. What we'll see in later intuition lectures is that we can do this for second order, first order, pseudo first order, catalytic reactions. I'm just giving you the bare bones introduction here, and we're doing that for the first order process. What I haven't mentioned yet in specific detail is the graphical rate equation. So if we change the rate constant again, what we can see is that that graphical rate equation is changing as well. So the rate of formation of product versus the concentration of product. We can do this for rate concentration. Sorry, excuse me. It's the concentration of A versus the rate of formation of product. So what we can see here, taking that a little bit more slowly, is that as you increase the concentration of A on the x-axis, you are increasing the rate of formation of the product in a linear fashion. So as A increases, the rate of formation of product increases linearly. If you double the concentration of A, you double the rate of formation of product P. That, in a nutshell, is the characteristic case for a first order reaction. What you can then do, and what I'll provide separately from this, is you can once again take out the raw text information that is embedded within these plots, put them into Excel, and co-plot them together. One of the things that's a little bit tricky in COPASI is that sometimes it's a little bit too clever for its own good. As you update the rate constants, the scale of the x and the y-axis might change, and COPASI tends to do that dynamically and automatically. So the graph might not look like it changes a lot, but it's because COPASI is trying to optimize the axes on your behalf. So if you take the data out into Excel or some other spreadsheet package, then you can co-plot various different simulations on the same graph with the same axes so that you can compare the magnitudes of change more directly. For now, I hope that's given you a sensible, meaningful, and not very intimidating introduction to how you might use a kinetic simulation software package like COPASI in order to look at simple reaction mechanisms. Note here that I've not once described a single chemical example under the hood. We haven't really looked at the mathematical formalisms, either differential or integral equations for a first order process. I have deliberately focused on the fact that you can simulate this, you could propose the first order reaction and start to build up your intuition, start to build up graphs that you can change and get feedback on without knowing either of those things, without knowing a mechanism, without knowing a particular chemical case, without knowing how to write down the mathematics. This is often what I found to be the intuition I was missing when I was trying to learn mechanism. But what we've done in this intuition lecture is to show you how you can do those 1,000 experiments, those 1,000 mechanistic experiments, before you ever go into the lab, before you ever run a quantum chemical calculation. Thanks very much for tuning in. If you've got any feedback or questions, please let me know in the comments or by email if you're taking the course in the university. And I'll be sure to clarify and update this where I possibly can. Future intuition lectures, as a reminder, will include more complex examples of how we can use COPASI to look at multi-step and higher order processes. I'll see you again soon.